Welcome to the Chapter 4 lecture for the Management 3120 Operations Management course. I am Dr. Bill Perkins, and I'm going to provide you a video lecture based on the material found in the textbook Practical Operations, 2nd edition from Natalie Simpson and Philip Hancock. So our objectives for this chapter is to explore the approaches to forecasting. We're going to develop an ability to evaluate forecasts and understand the importance of putting forecasting tools to work. So let's get started. So the word forecasting describes almost any attempt to anticipate the future. You probably have heard it used for such diverse activities such as economic forecasting, weather forecasting, for example. Now, in operations management, forecasting is more specialized, usually focusing on one particular outcome, such as future demand on a given operation. So basically, for the purpose of this course, forecasting is predicting future events, but relevant to operations management. Now, figure 4.1 here, illustrated on this slide and taken from page 104 in the textbook, summarizes broad categories of forecasting methodologies that a manager might choose when attempting to predict a demand on an operation. So each of these approaches suggests specific techniques, and each of the techniques has differing advantages and disadvantages. So as figure 4.1 suggests, the first and most strategic choice when selecting a forecasting technique is whether to use qualitative or a quantitative approach. Now, a qualitative approach attempts to capture human intuition, such as an expert's insight, when developing a prediction. Now, pictured here at the left side of the branch of the forecasting map in figure 4.1, qualitative techniques are structured methods for gathering the insight of forecast participants. Now, how this insight is gathered and who exactly provides the insight varies among the techniques mentioned in this figure. So you have examples such as surveys, expert opinion panels, and Delphi groups, which we're going to get into here in a minute. Now, one method of gathering insight into the future is survey research, including customer surveys and market research. Now, this method poses questions to large numbers of people believed to have some knowledge of the outcome of interest, such as potential of customers of a product. Now, these questions may be posed through web-based forms, paper-based questionnaires, or personal interviews, with the resulting answers compiled and interpreted into a forecast. Now, web-based technology in particular can support the process of what's called crowdsourcing, as mentioned on this slide, a potential forecasting tool. Crowdsourcing allows for the rapid generation of forecasts by averaging large numbers of independent responses to a single question. So crowdsourcing is defined as combining independent efforts of many people to accomplish a task. Now, whereas surveys and crowdsourcing rely on the collection of insight from large numbers of people, expert opinion panels rely on much smaller groups believed to have superior knowledge of the future outcome. So when these experts are all leaders and managers, the group may then be referred to as an executive opinion panel or a jury of executive opinion, as defined on this slide. Now, an expert opinion panel brings its participants together to discuss the outcome of interest and then develops a prediction from the panel's consensus view. So an expert opinion panel is a small group of highly knowledgeable people who develop prediction through discussion and consensus. And a jury of execution opinion is an expert panel composed of managers. Now, like expert opinion panels, Delphi groups rely on a small number of experts to create a forecast. However, unlike expert opinion panels, Delphi groups never discuss their opinions and may remain anonymous to one another even after the forecast is completed. So this method, therefore, is theoretically, it removes the bias. Stronger personalities or more influential members of the group do not have the opportunity to sway the opinions of fellow group members. So Delphi method is a qualitative forecasting technique in which experts achieve consensus through a blind process via a facilitator. Now the facilitator sends each participant the forecasting question, and let's say they gather the participants' responses. Then they create an anonymous report of those responses and distribute this report back to the participants. So then after the participants have read this report, the facilitator asks the question again, then gathers a second set of responses, and they create a second report, and they distribute that report back to the Delphi group members. Now, because participants are encouraged to revise their answers after reading each report, this process repeats until consensus is achieved. Now, quantitative forecasting relies on mathematics to develop predictions. Specifically, this approach relies on identification of useful relationships between a future outcome of interest and any other known factor or factors. Now, figure 4.1 here illustrates two important branches within this type of analysis, associative models and time series analysis. Now, in general, associative or causal models identify relationships between an outcome of interest and one or more factors that might be used to predict an outcome. Now, associative models are therefore based on two types of variables. The dependent variable is the outcome that depends on or is influenced by outside factors, and those external influential factors are in turn referred to as the independent variable. So causal modeling is predicting an outcome by identifying its relationships with one or more other factors. So forecast managers often begin to investigate associations by visualizing the data as scatter plot diagrams or on scatter plot diagrams, such as the one illustrated here in figure 4.2, and this is also seen on page 106 of the textbook. Here the dependent variable is the delay between a drug's injection and the relief of the patient's symptoms, or the needle to symptom relief time. So figure 4.2 suggests a distinct association between this variable and the delay of the same injection from the onset of the patient's symptoms or the symptom to needle time for 30 patients. Now, specifically, the upward direction of the cloud of points describing the past 30 patients suggests that the longer the delay until the injection, the longer the actual time until relief after the injection. Now, knowledge of this relationship helps optimize the care of future patients. While visual examination of such graphs suggests many relationships, mathematical techniques clarify and quantify the links, as we will see later in this chapter. So where associative modeling attempts to predict a future outcome by identifying important links between the outcome and other factors in its environment, time series assumes the future outcome is simply a function of that outcome's historical behavior. Thus, this approach focuses on past data in an attempt to project this behavior into the future, which is a methodology known as extrapolation. So extrapolation is simply projecting existing data into the future. Now, a time series is a set of observations of a particular outcome at regular intervals in time. This is creating a history that can be illustrated as a line graph. So time series are a set of values observed in chronological order. So in this example in figure 4.3, the outcome of interest is the total number of new housing construction projects or housing starts in the U.S. as observed every month from January 1959 and June of 2016. So figure 4.3 suggests that monthly U.S. housing starts may be the result of several distinct influences, such as the rhythmic peaks that mark summer as the busiest months for construction, or the broader rise and fall of those peaks in longer economic cycles. So in general, time series analysis includes a process for clarifying these influences known as time series decomposition. We will discuss this taking apart of existing historical data to expose its component influences later in this chapter. So because so many forecasting techniques are available, it makes good sense to evaluate them to determine which particular technique is most desirable for a given situation. Successful forecasts may lead to competitive advantage, so it is no surprise that we base our evaluations on accuracy, responsiveness, and costs. Though none of these measures should be considered in the absence of the others, accuracy is the natural focus of forecast evaluation. Now I'm going to address accuracy. Accuracy is the central measure of success in forecasting. So once we create a forecast, we must wait to see the actual outcome to determine the quality of the forecast. Accuracy can be expressed in several different ways, including common performance measures of error. You have mean error, ME, mean squared effort, which is MSE, and mean absolute deviation, MAD, and tracking signal, and mean absolute percent error, MAPE. So error is the simplest measure of forecast accuracy. Figure 4.4 here in this slide shows a portion of a spreadsheet with the actual data from the previously covered figure 4.3 a couple slides ago, compared to naive forecasting of housing starts in each of those same months. In a naive forecast, forecaster assumes that the next future value, such as the number of housing starts next month, will be the same as the most recent known value. In this case, the number of housing starts observed in the current month. Now, this forecasting technique is simulated for 690 months in the figure 4.4 spreadsheet model, and the forecast error associated with each of those months appears in column E of the spreadsheet. Averaging forecast errors over time results in the performance measure known as mean error. Now, figure 4.4 displays the mean error that results from averaging all values in column E, most of which are not visible in this sample view. Now, while an error of 0 indicates a perfectly accurate forecast, an average error of near or exactly 0, such as mean error of 0.02 in figure 4.4, does not necessarily signal accuracy. So as you can see in column E in figure 4.4, substantial forecasting error occurred within the first year of the time series for U.S. housing starts between 1959 and 2016. Therefore, we would be premature to declare these naive forecasting values accurate based solely on a near zero mean error. The positive and negative error values canceled each other in the calculation. Now, ironically, while this renders mean error an unreliable measure of accuracy in this case, it also makes a mean error an excellent measure of forecasting bias. So again, mean error is the difference between an observed value and a predicted value. And forecasting bias is a tendency to make forecasting errors of a certain type, such as consistently predicting too high or too low. Forecast bias is central to forecast evaluation because we can control for any error made consistently and thereby make more accurate forecasts in the future. So remember, forecast bias is the tendency to create errors that are predominantly positive or negative. Now, because we cannot rely on the accuracy of data based on mean error, we need another approach. One approach that prevents obscuring of errors is to square each forecast error, producing a non-negative value. So when all squared errors are averaged across a set of forecasts, the result is a performance measure called mean square error, or MSE. Mean square error is an average of the squared values of a set of forecast errors. Another measure of forecast accuracy is to consider absolute errors only, dropping the issue of positive or negative deviation in a forecast. Averaging such observations into the single value known as mean absolute deviation, or MAD, provides the same benefits as mean square error, but without exaggeration of larger errors. Again, mean absolute deviation, or MAD, is an average of the absolute values of a set of forecast errors. Now, to get a better sense of the quality of a forecast relative to the actual values being forecast, forecast error is often translated into percent error. Now, percent error is the forecast error divided by the corresponding actual value. And the mean absolute percent error is the average of the absolute values of a set of percent errors. A forecaster concerned with monitoring potential bias over time could consider calculating a tracking signal periodically. The tracking signal is the ratio of the sum of a set of forecast errors over the MAD of that forecast. Now, demand forecast errors often cause excess or shortage in reality. Here, an input error generated unintentionally low forecast for a particular class of dried pasta at the supermarket. The telltale result is this conspicuous gap in the shelf space within the pasta section, as the stock requested based on the inaccurate forecast numbers has been depleted unnaturally early. Now, a regression analysis clarifies relationships between a dependent variable and one or more independent variables. So linear regression focuses specifically on the paired relationship of a dependent variable and one independent variable. This type of influence was suggested earlier by figure 4.2, in which the amount of time that lapses between the onset of a patient's symptoms and the injection of a drug appears strongly related to the amount of time the patient must wait for relief from the symptoms. So regression analysis involves using mathematical relationships between two or more variables to predict future values. So these two delays, when plotted as coordinate points for 30 patients, suggest an upward sloping line indicating that the longer a patient waits for an injection, the more time the drug then requires to bring relief. So figure 4.5 here shows the same data as figure 4.2, but includes a straight line that best describes this relationship. Restated, figure 4.5 displays the one straight line that minimizes the squared errors between itself and the actual data points. Thus, the process of identifying such a line is also known as least squared regression. Any line or linear relationship can be stated as an equation. Displayed here is a S-slope intercept format where where A is the y-intercept of the line and B is its slope of the graph. In the case of figure 4.5, this equation y equals 36.623, and we're going to add it plus 0.9661, which is the x, implying that needle to symptom relief for a patient might be estimated by multiplying that patient's symptom to needle time by 0.9661 and adding 36.623 minutes to the result. The slope alone, b minus 0.9661, implies that for each additional minute the injection is delayed slightly less than 1 minute, more of a delay until the relief after the injection occurs. A correlation coefficient is a value that expresses both the strength and direction of a linear relationship. It is a measure of strength of any linear relationship between two sets of observations. And another measure of strength of a linear relationship is its coefficient determination, or R squared. A coefficient of determination is a proportion of variation in a dependent variable that is explained by a regression model. Now, one helpful process in time series analysis is time series decomposition, or the disassembly of historical data into a group of component influences that hypothetically combine to create the actual values observed. So theoretically, any time series can be taken apart to examine its components, and knowledge of the components and their relative importance can be used to anticipate future behavior of the series. And trend is any sustained linear growth or decline across a time series. Although every data point within the series does not necessarily grow or decline when compared to its neighbors, trend analysis is a specific application of linear regression that hypothesizes that y, the dependent variable, can be predicted through its linear relationship with x, the passage of time, where the passage of time is expressed as values on a number line. Now, while a linear trend is not a significant influence across time, how much of the intricacies in actual monthly housing starts results from strong seasonality within this series. Seasonality is any pattern of a high or low values that consistently repeats within a time series. The sale of Christmas trees is a perfect example of seasonal pattern of demand. And cyclic variation is a pattern of growth and decline that is recognized as separate from seasonality, distinguished by the fact that the pattern may take several years to complete, and the length of this long pattern will not necessarily be the same each time it cycles. So remember, cyclic variation is seasonality with a cycle longer than 1 year, generally associated with economic influences on time series data. Construction activity follows annual cycles in many regions due to its unavoidable exposure to the environment. And this infrastructure project is a good example, as the concrete necessary to complete these drains will only set reliably within a certain range of air temperature, and the personnel working below ground must be wary for the potential for heavy rain in that area. So furthermore, this particular industry is of interest to forecasters elsewhere, in that the overall rise and fall of construction activity often reveals the broader cyclic variation of a local and national economy. While trends can be quantified and projected forward with linear regression, the nonlinear nature of seasonality requires a different approach. Once seasonality is recognized, a set of seasonal relatives can be calculated to express the pattern. So seasonal relatives are a set of numerical values that describe a seasonal pattern. Okay, so we're just going to go over our chapter here. So in summary, forecasting refers to most any attempt to predict an outcome, although forecasting and operations management usually focuses on anticipating some form of future demand on the operation. Forecasting approaches can be either qualitative or quantitative, relying on either human insight or mathematical models, or maybe a blend of both. Qualitative techniques tend to be more expensive, but quantitative techniques must be supported by a supply of relevant historical data, which may not be available in some situations. Nonetheless, quantitative techniques are more common in operations management in that an ongoing operation usually generates past data needed for this approach. Now, forecast accuracy can be measured in a variety of ways, although accuracy is not always the sole issue of concern when using a particular technique. Now, the issues of responsiveness can even direct the cost of the technique, and the technique is very important to the methodology. So the issues of responsiveness and even the direct cost of the technique may be important as well. Now, popular quantitative techniques can be divided into associative models and time series analysis. Associative modeling, such as regression analysis, identifies significant relationships between an outcome of interest and some factor or factors that are hypothesized as influencing its behavior. Now, once these relationships are expressed mathematically, the resulting regression equation can be used to estimate further values of the outcome based on known values of the other factors. Now, in contrast, time series analysis forces on the behavior of the outcome over time in an attempt to project that behavior into the future. So time series analysis relies on the idea that the actual behavior observed in the past is created by a combination of component influences such as natural variation, trend, seasonality, and cyclic influences, and exogenous variation. Attempts to identify and quantify these components are then attempts to take apart the past data, a process known as time series decomposition, and time series techniques such as moving averages and exponential smoothing are fairly simple, although better adapted to forecasting outside the influence of trends and seasonality. So smoothing techniques may even prove useful to historical analysis because of their unresponsive tendencies under certain conditions. And that concludes our Chapter 4 lecture. Please tune in to Blackboard to look for this chapter's expectations and deliverables, and I will see you in Chapter 5.